So lesson 7.3, we're going to be looking at exponential decay coming from 7.2, where we looked at exponential growth. We spent a lot of time this year looking at straight lines that have a slope, and those represent a constant increase or decrease. So these do not have a constant increase or decrease. They're going to go up at an exponential rate, or we're going to have exponents, and there's going to be a curve that creates a decay. So it's going down at a changing rate. All right, so it's actually going to be using the same formula that we were looking at. So our big idea, decaying at a constant percentage rate, can be described by an expression of the form b times g to the x, which looks very similar to what we did for exponential growth. But if you remember, for exponential growth, g had to be a number greater than 1. So for decay, g is greater than 0, so we're not looking at negatives, but less than 1. So numbers between 0 and 1, you're talking about fractions, decimals. And the variable is in the exponent. That's what's changing. And we've talked about that's the time. Okay, so if you think about when you multiply by something like 0.5 or 0.6 or a half or 3/4, it makes things smaller. And so that's why this is going to represent decay. All right, so things are going to be getting smaller. And if you take a look, we'll come back to these graphs in a second, but exponential growth, where g is greater than 1, this number, when you multiply by a number greater than 1, it gets bigger. And it's being increased by an exponent, so it gets bigger very fast, and so does our value. All of a sudden, it's not a straight line, it's not a constant increase, it's going to increase exponentially. And then today we're going to be looking at decay, so it's the same exact equation, but that number that goes in for g is between 0 and 1, so a decimal or a fraction in there. And if you think about, again, multiplying by those types of numbers, that creates a decrease. All right, it is being raised to an exponent, and it's going to create a curve that's opposite of the growth. It's actually going to start off falling faster, and it's going to slowly fall less and less and less. All right, so exponential decay is a decrease over time. And again, it's going to use this same formula, y equals b times g to the x. Let's define these variables. Y is your total amount. B is your beginning amount. G is still your growth factor. X represents number of time periods, so that hasn't changed. But the most important part of this whole thing, for this to be decay, g is between 0 and 1. Okay, so as soon as we change g to a number that's between 0 and 1, we have decay. When g is greater than 1, we have growth. Now we're going to be talking about half-life, and this is kind of a science term. You'll definitely talk about this in your science classes. But when things have a half-life, you've got a substance, you have a material, and it decreases, it decays. So a half-life is the amount of time it takes half of the material, which makes sense, half-life, to decay. So you're going to have some material that's decaying, meaning it's kind of disappearing, it's going away. And a half-life tells you how long it takes for half of it to decay, half of it to go away. And it's not going to go down at a constant rate where, let's say half of the original was 50, it's not going to go down by 50 again. It's going to go by down half of the new amount. So if you were at 100 and at half-life down, you're going to be at 50. But now when you get half of that, that's 25. Now you're at 25. Half of that is 12 and a half. So it goes down that. So you keep taking half of something. You're not taking a constant amount, but you are taking a constant percentage. All right, so the value g determines whether the equation describes growth or decay. Third situation could happen where there is no change. We could still have this equation. Okay, so it doesn't have to be the equation of a line like we're used to saying. We could have this equation. If g is exactly 1, it doesn't matter how many times you raise 1 to a different power. It's still 1 times 1 times 1. It's still 1. And when you multiply anything times 1, it doesn't change. So what that's going to look like on a graph is one of these horizontal lines. Okay, y equals something, just a number. All right, so it is possible for one of these equations in this form to create a straight line, but only when g is 1. G is greater than 1, shows growth. G is less than 1, of course, greater than 0. We're not looking at negatives here. That's going to be decay, which is a decrease. So going down to example 1, can we look at the equation of a function and determine whether it's exponential growth, exponential decay, a constant increase, or a constant decrease? So remember, these constant increases and constant decreases, those are lines. Okay, explain your reasoning and sketch what the graph could look like. So starting with something we've been working with all year, y equals 5x plus 3. That's in y equals mx plus b form. We don't have any exponents, right? We're not raising anything. So this right here has a slope of 5. Slope means that's what it goes at. That's the rate of increase the entire time. Since it's positive, this is a constant increase. That's what the first thing they wanted us to do. Tell whether it's exponential growth, exponential decay, a constant increase, or constant decrease. This is a straight line, no exponents. The slope is 5, which represents a constant increase. Explain your reasoning and sketch what the graph could look like. Explaining my reasoning is showing right here. This is in the form y equals mx plus b. The slope is 5. And a positive slope has a line that goes up, straight line, right up your graph. All right, next one. We've now got it in this form. Y equals b times g to the x. The number right here, g, is 3. So if it was a 1 in here, this would be a straight line, but it's not. G is greater than 1, and that represents exponential growth. So anytime we have g being greater than 1, that's exponential growth, and that's going to look like this. It starts off growing, and then it gets faster and faster and faster, and it starts growing at a much higher rate exponentially. All right, when we take a look at the next one, also in the form y equals b times g to the x. It's exponential. There's an exponent there. The g, like here, the g was 3. The g is 1.3. Well, g is greater than 1. So this also is exponential growth. What does that look like? Increase that gets greater over time. Curved line. Okay, we come to the third one. This is in y equals mx plus b form. That's a straight line. We can identify the slope. It's right here, -3. So first of all, if it's a line, it's going to have a constant increase or decrease. And if the slope is negative, this is a constant decrease. It's going down. But it is constant. So on the graph, this is a straight line. It's not curved, going down. All right, and last but not least, we have another equation here that's in the form y equals b times g to the x. Looks like exponential growth or exponential decay. The number in here is not 1, so this is going to be either growth or decay. So g is 0.5, and that means g is less than 1, and of course greater than 0. And so this right here, this represents exponential decay. This is something that is decreasing over time, but not at a constant rate, and it's going to create a curved line on the graph. Okay, so we need to be able to identify what these look like as an equation and what they would look like on the graph and what they could represent in a real life problem. So let's flip this over, and we're going to go to example number 2. So assume that each day after cramming, a student forgets 20% of the vocabulary words learned that day. A student crams for a Spanish test on a Friday by learning 100 vocabulary words. That's what they're starting with. That's important information. On Thursday night. And then due to a snow day, the test is delayed until Monday. If the student does not study over the weekend, how many words are they likely to remember for the test? Okay, so they're not losing a certain number of vocabulary words in their brain, a certain number every single day. It's a percentage, 20%. And we know percentages change based on how much you have. Okay, so this is going to be in the form y equals b times g to the x. If you think about it, they're losing. This is going down. This is decay. Forgets. That's decay. They're not learning more. They're not increasing. They're decreasing. This is decay, which means when we plug in for g, it needs to be a number less than 1. Now, we know 20% is 0.2. But if we multiply by 0.2, we get 20%. So it's not saying that all of a sudden it goes down to 20% of what it used to be. It loses 20%. So you're starting off with 100%. So I'm not talking specifically about these 100 vocabulary words. I'm just talking about 100%. So if for G you had 1, that's 100%, and you're losing 20%, that means G is going to have to equal 80%. Let me go through that again. You're losing 20% every single day. So it doesn't go down to 20%. You're losing 20%. Whatever you start with is your 100% or 1. And when you lose 20%, you're now at 80% of what you used to be. Okay, so the decay, what it's going to go down to is 80% of what it was each and every day. So when we plug in here, B is what you started with, your beginning. So you started with 100 vocabulary words that you knew. And then your growth factor here, what it's going to go down to is 80% of what it used to be every single day. So you're timesing this by 80%, so 0.80. And you can just call that 0.8. And it's every single day. And so X is how many days. So again, you're losing 20% every single day, but that's not going to be the same amount every single day, because when you have less, 20% of a smaller number is actually a little less and a little less and a little less. So you're not losing the same number of words every single day. You're losing the same percentage of words. So we need to see the difference. Now in this specific one, what number are we going to plug in for time? So Thursday night they cramped. They were supposed to take the test Friday. They went all day Friday. They didn't take the test. That's one day. Saturday, Sunday, it's now Monday. So that's 4 days. And so we're going to plug in 4 here. So it's 100 times 0.8 raised to the 4th. Run that out and you're going to get 40.96. And so we're going to say about 41 vocabulary words. Think about if it was just one day. If you started with 100, after one day, they've forgotten 20% of that. So 20% of 100 is 20. And so how many words would they know? They would know 80. So if they had taken it Friday, only one day since they studied, they would know 80 words. But by the time Monday comes around, again, it doesn't go down 20 every single day, 20%. Okay, 20% of 80, then 20% of that number. We've gone down by Monday to 41 vocabulary words. All right, example number 3, same idea. In 1998, a new car cost, so there's the year, here's the original cost, $21,000. Its value depreciates, that's going down, at a rate of 15% per year. So there's all the information that you need. Find the equation that gives the car's value, y, when it is x years old. So we don't know the numbers here. We want to know the car's value, so y equals, now first of all, it's going down by a percentage, so we need to know that when you go down by a percent or go up by a percent consistently over time, that does not create a straight line. So this is going to be b times g to the x. That's the equation we need. And now let's plug in the information that we've got. So they want to know, find the equation when the car's value, which you're going to represent as y, so y equals, we're also going to have an x here for the years old, for any number of years old. So B is your starting amount, 21,000, times your growth factor. Now, it's depreciating 15%. Here's where most of you are going to make your mistakes. You're going to put 15% here. But it's going down 15%. So if you were at 100%, which is 1, and you go down 15%, you are now at 85%. So we need to find 85% of 21,000 after 1 year. So 85%, because think if you were raised to the first 1 year, you're taking 85% of this. It's not going down to 15% of what it used to be. That would be a huge drastic change. The car just goes down 15%, a little bit, every single year. So when you go down 15%, you're now at 85% of what it used to be. And that'd be 1 year. And every year, it goes more and more and more. And so we're going to represent X as the number of years. And now we can answer letter B using this formula. What's the predicted value of the car in 2005? Well, this started in 1998. So 2005 minus 1998, that's 7 years. Okay, so we're just using this formula to figure out what's going to be the new value of the car 7 years later. So you're starting off with y equals 21,000. 85% of the price every single year over 7 years. Now, when you run this in your calculator, you're going to get a really long decimal. And you always have to look at the context of the question. This specific question is talking about what? The value in money. So we do need to round this. So we're going to say $6,732, and it's 11 cents, but the 8 bumps it up, 12 cents. So this should seem a lot like exponential growth. Okay, it's using the same formula. The difference is, if you think about growth, we never even plugged the percentage of growth in for G. We always added it to 100%. So it was always 1 point something. But now we are going just the opposite direction. Decay takes it off. So our growth factor is not 15%. It's 15% coming off of 100%. And so it's now 85%. So that's going to be the one part we need to get used to. Exponential growth, add the percent to 1 or 100%. And exponential decay, we're taking it off of 100%. We're losing, we are depreciating. So you take your 100% minus this, and your growth factor is what is left.